Our second talk is going to be given by Professor Yifan Cui from Zhejiang University. Unfortunately, he cannot come in person, so we have the talk online.
Great. Thank you, Kun, for the very kind introduction. And it is my great pleasure to present our work at Pacific Causal Inference Conference. So today, my talk is about proximal causal learning of heterogeneous treatment effect. So in this talk, the outline will be I will first briefly review the unconfoundedness, this important concept in causal inference, and then talk about what is the proximal causal inference and proximal identification. Then I will also talk about the doubly robust proximal causal inference and our proposed p-learner to estimate heterogeneous treatment effect. Due to the time limit, I might skip the last two parts on the individualized decision-making and the survival analysis. Let's now suppose we observe RID samples. The data is AYL, very standard setting. The A is the treatment of interest, and Y is outcome of interest. We are interested in analyzing the causal effect of the treatment A on outcome Y. And L is a set of measured covariates, including such as age, gender, etc. And let Y little a denotes the potential outcome, the standard notation. And suppose we are interested in estimating the average treatment effect. One essential ingredient is to identify and estimate this counterfactual mean beta A. It is well known that under the consistency, positivity, and unconfoundedness assumption, this counterfactual mean beta A can be identified by the last equation, also known as the G formula in the literature. So beta A can be expressed by the observed data. So for the observational study, researchers might question this unconfoundedness assumption because it is a not testable assumption. So let's now look into this unconfoundedness assumption. When we think this unconfoundedness assumption given L, we will firstly think about the figure A. Most of us, I guess, the L includes all causes of treatment A and outcome Y. Okay, but in fact, unconfoundedness is more general than that. For example, in figure B and the figure C, the unconfoundedness assumption given L also hold. For example, in figure B, though you have an unmeasured factor U, here L includes all causes of A that share an unmeasured common cause U with Y. So this unconfoundedness given L still holds. Okay, for the figure C, though you have unmeasured factor U, the unconfoundedness given L also holds. Here, L includes all causes of Y that share an unmeasured common cause U with A. What we'll call this in figure B, this L as type B proxy, and the figure C, the L is type C proxy. And in a figure, these three types of proxies might coexist. For example, in this figure D. Here, the unconfoundedness given the L also holds. You don't need to classify the L into these three buckets, type A, type B, type C proxy. So if you do a regression or lasso or neural nets, you regress Y on the L and A, you get the correct causal answer because there is no backdoor path from A to Y. Okay, unconfoundedness given L still holds, but you need U1 and U2 be conditionally independent given the covariates L and A. For example, in figure E, if U1 and U2 share an unmeasured common cause U3, then the unconfoundedness given L doesn't hold because there is a backdoor path from A to U2 to U3 to U1 to Y. So proximal causal inference is one candidate method to do the causal inference when this unconfoundedness assumption doesn't hold. In the literature, many methods, including instrumental variable, invalid IV, etc., have been proposed. So here in this talk, I'm going to focus on the proximal causal inference, this framework. In the last figure E, there are U1, U2, U3. It's too complicated. Let's combine them as one U. And I will use this figure to illustrate the proximal causal inference. But there are many sufficient graphs which can be used. I will just pick this one. So here, the proximal causal inference, the essential idea is to replace the unconfoundedness assumption with the following assumption 1. So the essential idea is to correctly classify this observed covariance L into that 3 buckets, type A, type B, type C proxy, so that assumption 1 holds. So the first line of the assumption 1 is the conditional independence of Z, and the second line is conditional independence of W, and the last line is the latent unconfoundedness. So for this latent unconfoundedness, you can always find U so that this unconfoundedness assumption holds. So less crucial than the first and the second line. So we need to find the proxy, this ZW, so that the first line and the second line, the conditional independence holds. So these are mathematical conditions, not much to say, but there is a causal interpretation here. So the conditional independence essentially requires that Z does not have a direct causal effect on Y, which means there is no direct arrow from Z to Y. And the conditional independence of W essentially requires there is no direct causal effect from Z to W, no direct causal effect from A to W. Okay, so in the observational studies and real-world data, there are many such proxies, and the one leading example is the longitudinal data. For example, at a given time point, the A is the current treatment and Y is the current outcome. Then you can pick this W as a previous outcome, and you can pick this Z as future treatment. So if you believe the future will not cause current, current will not cause past, then this assumption 1 holds. Okay, so you might say that this future treatment Z might not cause the current treatment. It doesn't matter. You can have the arrow from Z to A to Z, or there is no arrow between Z and A. It's fine. You can check. They all satisfies assumption 1. Okay, so suppose we can correctly classify the L into these 3 buckets, X, Z, and W. How do we achieve the identification? Let's now look at one motivating example, use this linear structure equation. Suppose Y given Z X U is linear, so you can drop the Z because of the conditional independence assumption. And the W given Z X U is also linear, you can drop Z and A. Here, we want to identify the beta A. After some simple calculation, you can get the expectation of Y given Z X equals to beta 0 star plus beta A times A plus beta U star times the expectation of W given Z X plus the beta X star transpose X. So there is no U here. So this equation is in terms of observed data. So we get the identification of beta A. And in practice, you can do a 2-stage least square. You can regress the W on ZAX, and then regress the Y on A, W hat, and X to estimate this beta A. So this is similar to the 2-stage least square in the instrumental variable method. Nowadays, we talk about this machine learning data science, so we kind of want something non-parametric. So here is the first identification result through the outcome confounding bridge proposed by Mill et al. 2018 biometric paper and Croquet and Pro 2014 biometric paper. So they assume this assumption 2. The assumption 2A is about suppose that there exists an outcome confounding bridge function H that solves the expectation of Y given ZX equals to expectation of H given ZX. Let's assume it for now, and we will take a look at the implication in 2 slides. And we also assume this assumption 2B here is the completeness assumption. For any function G, the expectation of GU given ZAX equals to 0 if and only if GU equals to 0. So this essentially requires the left-hand side implies the right-hand side because the other direction is trivial. Okay, let's also assume it for now. And combining this assumption with assumption 1, which you can correct classify L into X, Z, and W, you get the identification of the counterfactual mean and every treatment effect. So beta A can be written as the expectation of H. And as the intermediate result, you have the expectation of YA given U and X equals to expectation of H given U and X. You don't need to restrict the distribution of U. And if you marginalizing over U and X, you get the first line. Okay. So now we have the identification, but let's now look at the implication of these two assumptions. So for assumption 2A, is essentially requires the existence of the solution of the well-known Fredholm equation of the first kind. So the mathematical condition for this is well studied in functional analysis. I'm not going to the technical details here. And in the next slide, we can take a look when Z, W, and A are all binary. What does this condition say? Okay, the assumption 2B, the completeness assumption, on a very high level, you can think you use this information to recover use information. So you want the variability of this random variable Z be larger than the variability of U. Okay. So for example, if Z and U are categorical, you can actually solve this condition using the system of equations. If the matrix is full rank, then if the number of equations is more than number of parameters, you don't have non-zero solution. So you mean it requires the number of categories of Z is larger than the number of categories of U. And there is analog for the continuous Z and U under certain model. Is you want the dimensions of Z is larger than the dimension of U. Okay, let's go back to the assumption 2A again to look at when the A, W, and Z are all binary. What does this condition say? So here, expected is not an integral equation anymore. It's just a sum, and by very simple calculation, you get the closed form of H, and the G is defined in the following way. The last line. So we want the existence of this H. Essentially, we want the denominator of G is non-zero, which is about the conditional dependence between W and Z given A and X. This is an important aspect of the proximal causal inference. And here, for this very simple example, A, W, and Z are binary, we have closed form solution. But in general, because we want to solve an inverse problem, so we don't have a closed form solution. How do we solve this H? In our paper, we propose the proximal G computation is essentially using MLE. For example, we can specify the parametric model of this H and the parametric form of the joint density of covariates and treatment. We can use the MLE to solve the H and plug in to get the estimation of the counterfactual mean and average treatment effect. And in fact, things can be simpler is when does not need to impose a parametric form of the joint density of treatment and the covariates. It's because assumption 2A implies a moment restriction. So the expectation of y minus h times this function m equals to 0. So how many parameters, you use how many equations, the method and the theory of the generalized method of moments can be applied here. Okay, this is about the identification and estimation using the outcome compounding bridge. And then let's move on to this treatment compounding bridge. So we propose this treatment compounding bridge identification, and we propose this assumption 3. So the 3A requires that there exists a treatment compounding bridge function Q that solves the integral equation expectation of Q given W, A, and X equals to 1 over propensity score, the density of A given W and X. Again, here, the implication of the existence of solution is the same as before. In the paper, we discuss when the propensity score is logistic, what would be the form of this Q function. And we'll also require this assumption 3b is another completeness condition. So the expectation of GU given WA and X equals to 0 if and only if GU equals to 0. So we want the variability of W is larger than the variability of the U. Okay, together with assumption 1, which we also need to correctly classify the L into X, Z, and W, we have the expectation of Q given U, A, and X equals to the 1 over propensity score. The density of A given U and X. So we can recover this propensity score with U, so we will be able to identify the distributional results of the counterfactual variable. So we can identify survival functions, quantiles, etc. So here I only write it in terms of the mean scale. So we have expectation of Y given UAX equals to expectation of indicator of A times Y times Q given U and X. And if we're marginalizing over U and X, we get the identification of the counterfactual mean and the average treatment effect. This is about identification. For the estimation, if Q is known, we can just do a simple sample average to estimate the average treatment effect. However, in practice, Q is not known. So parametrically solving it, we notice that the expectation of Q times N is any function of WA and X minus NW1X minus NW0X. This expectation equals to 0. So again, we can use the GMM here to parametrically solve this Q. Okay, we will talk about how to solve it non-parametrically in the end. Let's now combine this Q model with the H model, and we derive the efficient influence function of the average treatment effect under this semi-parametric model, which further motivates our doubly robust estimator of the average causal effect. This psi PDR, which is consistent under the union model and is semi-parametric locally efficient in the intersection submodel. And here the doubly robust property refers to if one of the Q and H is correctly estimated, then the psi PDR is consistent. So I'm going to skip the technical details and the numerical results here, and rather let me highlight one connection of this efficient influence function with the efficient influence function under the unconfoundedness. Suppose unconfoundedness given L actually holds, so the U here is empty. Then we can write the H as expectation of Y given WA and X, and we can write Q as 1 over the propensity score density of A given Z and X. Then the efficient influence function, our efficient influence function, becomes the last line. And notice that given Z and X, A is independent of W. Given W, A, and X, Y is independent of Z. We are free to add the W in the propensity score and Z in the outcome regression. We can write Z, W, X together as L. Then the last line becomes exactly the same as the efficient influence function under the unconfoundedness. Okay, lastly, let me briefly introduce our constructed p-learner to estimate the heterogeneous treatment effect. Suppose we are interested in estimating this conditional average treatment effect tau x, defined as expectation of y1 minus y0 given x. So our p-learner consists of 3 steps. So the first step is to estimate the H and Q non-parametrically. So one can write the assumption 2A and 3A as a min-max optimization. And if we use RKHS to estimate H and Q, we have a closed form solution. So our second step is by using this doubly robust representation. So we construct the cross-fitted score using this H hat and Q hat. Here, the cross-fitted refers to when we construct the gamma I, we don't use the I sample. Okay, once we construct this cross-fitted score gamma, so we are able to transform the problem to a generic machine learning problem. So we minimize the empirical laws here. And our base learner talk here can be very general. We can use lasso, neural nets, random forest. And let's look at the visualization to get a rough idea of what we are doing. Here, I plot the estimated conditional average treatment effect versus the true conditional average treatment effect. 45-degree lines means the perfect estimation. This is a confounded setting, so the left panel causal forest is systematically biased, and the middle panel is our p-learner, is well aligned with 45-degree lines. And the right panel is oracle p-learner, which has smaller variance, but notice that it assumes a known H and Q, which is not feasible in practice. Okay, let me skip the last two parts and briefly summarize my talk. So proximal causal inference is a new framework for the analysis of observational data when this unconfoundedness assumption doesn't hold. And we propose this treatment confounding bridge and identification, as well as the proximal IPW estimator. And we also construct this proximal doubly robust and locally efficient estimator. And we also establish this p-learner to estimate heterogeneous treatment effect. And what I didn't mention is we did this optimal individualized decision making for the proximal causal inference, how to best use the information of the proxies W, X, and Z to make sharp decision. And we also did the survival analysis to estimate the marginal counterfactual survival curve. The talk is mainly based on those papers, and thank you, everyone.
Thank you very much, Professor Cui, for the very informative and concise talk. Thank you.
Thank
so
you.
you'll have time for one quick question. Or alternatively, you may just send email to Professor Cui to ask questions. Oh, okay. So Lin had a question.
Hi, Yifan. So thank you for the talk. So do you have any experience on doing this minimax optimization problem without the L2 regularization, like more generic minimax optimization?
You mean you want to impose another different regularization
right.
rather than the
stable or not numerically?
I think there are two different. One is a stabilized one, and the other is called regularization. There are two penalties there, right? In the min-max optimization.
Right. I'm just wondering if there's no closed form in some generic minimax.
Oh, I see.
Problem.
Okay, I only use the RKHS. So if for the more generic one, I might need to think about it more. Yeah.
Okay, thank you.
Yeah, thank you.
Yeah, there's one by Xiaojie and Missing Colors. I think they can allow for more general form. So one of the operation should follow some reproducing kernel Hilbert space, but the other does not need to follow that. So as far as I know, yeah.
Yeah, thank you.
So you can use anything. For example, you can implement it by neural network.
Mm-hmm.
You can look at the papers.
Yeah, thank you for the references. Sorry, I can't see who is talking, but yeah.
Okay, great. So we have to end this talk right now. Thank you very much, Professor Cui, and see you next time.